All right, so this is going to be reaction 4. I'm actually not going to do reaction 5. I'm going to move on to the Unit 2 study guide. The reason being, I don't like reaction 5 anymore. I thought I liked it, but I don't like it anymore. So I'm not even going there. So you can go ahead and stop at 4. And then go ahead and go to your study guide here. So this one is assuming you know some stuff. And this is where trusting yourself and understanding what you know is super, super, super important. Propane gas burns in a barbecue grill for cooking hot dogs and burgers. Assuming complete combustion, what are the products of the reaction? Now I know you are saying, that I can't do. They only give me one thing. They don't tell me any more information, but they do. Not only do they tell you propane gas, they tell you that it burns. That should be an indicator on a barbecue grill. I'm going to guess this is in the outside, not in a vacuum. It's not happening without any air present. Assuming complete combustion. Look at that. They're telling you the reaction. You should know some things. You should know that if they tell you it's combustion, then it's a combustion reaction. And our combustion reactions have oxygen in the product. Don't tell me there's no oxygen written, so I can't know it's there. It's in the air because you're at a barbecue and you're probably breathing at a barbecue, which means oxygen is present. And to go beyond that, it's probably the excess thing because I don't think you're going to run out of oxygen at a barbecue. And if you do, I have much bigger questions. So that's where I get my oxygen from. Now, it also tells me it's a combustion reaction. And so I know two more things. I know the products. I know the products for a combustion reaction are always, never changingly, CO2 and water. Now look at that. I have an almost complete reaction. There's a couple other things that's going on. Burns. Don't tell me, I don't understand if this is exothermic or endothermic here. Burning is hot. When you have fire, heat is being released, which means heat is a product. This should not be like news to you. You just have to apply what you know in this sort of chemical reaction format. So you have energy released in the form of heat at a barbecue, at a grill. It's pretty logical. You have water. It's going to be in the form of a gas. You have CO2, which is in the form of a gas. Oxygen is a gas. And the propane gas is actually, propane gas. So now, balancing. People have different ideas about this. In combustion reactions, you always want to balance oxygen last since it's only on one side of the reactants, and it's going to be pretty easy to figure out. So I say start with the things that are weird. The things that are weird are that you know that you either have to have 3 CO2 here, or it's going to be in some multiple of 3, 6, 9 because you have 3 carbons in propane gas. So I'm going to start with putting my 3 there because that balances my C's. Then I'm going to move over to my H's. I'm not worried yet about my any of the other molecules. So I have 8 H's over here, but I only have 2 over here, so I'm going to put a 4 there. That balances my H's. Now you just have to go through and figure out oxygen. So if I have 6 oxygen present in the CO2 and 4 oxygen present in the H2O, that gives me a total of 10 oxygen I have to account for. If they're diatomic, that means I need 5 molecules of diatomic oxygen. It literally tells you the type of reaction. It's a combustion reaction. It tells you that energy is on the outside because it's burning, which means that just like the one above, if I'm starting at 0 and 0, I'm not adding anything to the situation. Now, I know that you need a spark in terms of combustion, but sometimes that spark is not like you think of at a grill where you're actually like putting the flame over so that it catches. Sometimes that spark can be incredibly quick, so we don't consider that a constant heating or a constant input of energy. We're essentially just kind of kickstarting the reaction to go. And once that reaction is actually going, there's nothing that needs to be added to the system. That fire will burn until something goes away until either the propane gas is consumed or the oxygen is consumed. So again, we were talking about at church how you can put a candle out by putting something that covers that candle, and once all the oxygen is used up, the candle will immediately go out. So you have to be using up one of your reactants. So if we're converting chemical to thermal here, because again, producing heat, not adding anything to the system, yet again, we have more thermal. Chemical has decreased. That chemical leaves, or excuse me, that thermal energy leaves the system in the form of fire. It goes back down to 2 bars of thermal, 1 bar of chemical. Same energy curve as above. My reactants start at higher potential chemical energy than my products finish at. Okay, hopefully that was easy enough. Now, let's say that I have a 250 gram of propane tank. How many grams of each product am I going to create? I'm actually going to change that. Well, no, I'll go ahead and do it out. Oh, anyway. You could also just convert it to moles, but whatever. So it's multi-step. So the first thing that I have to do is I have to get into moles. Always. C3H8. I have to figure out what my mole ratio is. So that's 3 C's, which is 17 times 3 plus 8, 1 per hydrogen, which is a total of 44 grams of C3H8 is 1 mole of C3H8, which amounts, units cancel, which amounts to 5.68 moles C3H8. From there, I can figure out everything else. How do I figure out everything else? I hope you're shouting in your head right now, mole ratio, and I hope it's not just me going a little bonkers talking into a microphone. So if I start with, I have 5.68 moles C3H8. Handy dandy little trick here. Not what I wanted to do. Okay, so now I have to figure out the mole ratio for each thing. So let's say on this one, I'm looking for CO2. And on this one, I'm looking for water. So what I have to do is I have to apply the corresponding mole ratio. So I have to do this one at a time because they're different. So over here, excuse me, if I scroll back up to my reaction, 1 molecule of C3H8 will react with 3 molecules of CO2. So same thing on the bottom, 1 mole C3H8, so that the unit cancels, will react with 3 moles of CO2. Simple math says I'll get 17.04 moles of CO2. Great. If I want to convert that into grams now, I can come over here and I can figure out 1 mole of CO2 is how many grams of CO2. And guess what? Moles will have canceled. Now I'm in grams. Going to water. So back to my ratio. 1 molecule of C3H8 will give me 4 molecules of H2O. So I just reset the equation, keep my 1 mole of C3H8 on the bottom, cancels, is equivalent to 4 moles of H2O because that's the ratio. That's how many water molecules are made from a single molecule of C3H8 undergoing combustion. So that gives me 22.72 moles of H2O. How do I get that into grams? Well, I have 22.72 multiply 1 mole of H2O, so my units cancel, is 18 grams of H2O. And then I have some number of grams of H2O. Hope that was helpful. On to the study guide.